or related math areas.
Yes. Yeah. So, have you used Teams before? I understood that you installed it. You have not, right? Okay.
I already installed it. So
okay, can you try sharing your screen?
I'm looking at which option that would allow me to share the screen.
So there should be a square and an up arrow, and that's what at least I
open
see
share.
Right, yeah.
Give a try on that. Can you see that?
Yes, I do see your screen now. Perfect. Yeah.
Yep.
Yeah, I guess that's. Yeah, we're all set.
Hi, Ken. Hari here.
Hey, hi. Is it Harry?
Yes.
Yeah, how are you doing? Thank you, and thank you for joining.
Yes. We have a clash with another institute colloquium on neuroscience.
Oh, all right.
So some faculty may be going there. Don't know, or we'll hop from one to the other.
All right. So give me a little bit of time for that. Oh, sorry. Hold on. It seems to be a little bit strange with my computer. I basically use Zoom, but I'm trying to get myself accustomed to this Teams. Because usually when you use Zoom, when you make it full screen, you should be able to see your face as well, but I just couldn't see it.
Yeah, okay, that's an issue, I guess. With
so basically, they don't have this option. Yeah. Oh.
I hope you don't mind if we record this proceedings, right?
Oh, sure. You mean recording, right? No problem at all.
Yeah. And if it's available on YouTube, that should also be okay.
Yeah, I think so.
Okay.
No problem. Oh, so usually you would put this IIS seminar to the YouTube?
Yeah, nowadays we're doing that. Ma with us today. Professor Ma is a full professor at the Chinese University of Hong Kong. He obtained his bachelor's degree from the UK, and then he did his master's and PhD from the Chinese University of Hong Kong in Hong Kong. Professor Ma is an expert, well-known expert, needs little introduction, well-known expert for signal processing and communications. Well-known papers on MIMO transceiver design, matrix factorization for hyperspectral imaging, and remote sensing. Professor Ma is a fellow of the IEEE, and he has received several Best Paper Awards for his magazine articles, signal processing letters, and journal papers. Ken is also very active in the Signal Processing Society. He has been the member of the SPCOM Technical Committee and SPTM Technical Committee. He has also served on several editorial boards, signal processing letters, and currently he is also very busy being the editor-in-chief of Transactions on Signal Processing. So it's really a great honor to have you with us, Ken. And without further ado, I hand over the mic to Ken. Again, all yours.
Yeah, thank you, Sandeep. And thank you very much for inviting me. It's my great honor to give a talk at IIS. And Sandeep, you mentioned one thing that is very correct. It's very busy to manage transaction on signal processing, really. Anyway, now today I'm very happy to give a presentation on one of the very recent research that I and Mike, former PhD student and now postdoc, Mingjie Xiao, is doing, is about deep MIMO detection. Now, I should give a lot of credits to Mingjie because the most difficult part of the work were mostly done by him, while I watch and, if possible, try to provide some theoretical and fundamental justification or explanation of certain phenomenon. But I really like this work. Anyway, what problem do we deal with? Now, we deal with the classical MIMO detection problem. Now, for those who don't know what is MIMO detection, mathematically, it is a primary least squares problem with a well-defined data model that you deal with. Now, what we have achieved so far is that we train a deep net that can provide really good performance, almost optimum, for MIMO system as large as 400 by 400 binary symbols. Okay, and we did it in 20 layers. So in that regard, if you talk about the empirical talk, this looks very promising. Another very promising thing about this approach is that it works for the more emerging problem or research front of one-bit MIMO detection, which arises from the domain of massive MIMO. So how did we achieve this? Now, we didn't do things such as applying the deep neural net with very general structure like those multi-layer perceptron structure with many layers, very general renewal activation function without any structure, and you think that by using numerous GPU and servers, you will be able to find a good deep net. That is not what we do. We don't have all these very expensive facilities. We are using very simple method to do this deep network training. Now, what methods do we use? We use deep unfolding. Now, deep unfolding is a kind of deep network that has very strong structure and problem-specific structure. Now, the idea is to take insight from certain model-based signal processing or machine learning methods, and then take the structure, take the intuition to try to build a highly structured and possibly more efficient deep neural nets. And the first application of this deep unfolding was in 2017 by Samuel Deskin and Ami Rizzo. And thereafter, this topic has become very hot. And what we are doing here is to provide a different deep unfolding method. I will also give you guys a review on how this first paper performed deep unfolding. Now, but our approach in terms of the difference is that we are using a homotopy optimization method, which I will explain what it is, and then we are deep unfolding. Okay, so what revolves around this talk? I would like to share with you the insight behind. Either you talk about the insight behind non-convex optimization using homotopy to deal with this very difficult MIMO detection problem, as well as deep unfoldings. Now, but one thing, very strangely, don't ask me why it works. Now, because I don't want to fall into a pitfall, that is the following. When you see something working, you try to find reason to justify why it works well. Okay, so the pitfall that we can easily fall into is that we as humans easily see what we want to see. And therefore, when things are working by empirical means, it's easy for human being to find a confirmation of a theory when we are looking for it. Okay, so I, in terms of research style, do not want to fall into this part. So, but still, I will tell you the recipe that we use to enable us to get this deep neural net. Okay, so what problem? Now, MIMO detection problem, a very classical problem. It has many different scenarios for which MIMO detection can be applied. But the most well-known or representative version is that suppose on the transmitter side, you have multiple antennas, it sends multiple data, say binary, either -1 or 1. Receiver side, you also got multiple antennas. So, but you pass through a channel that form a linear mixing or entangling of the transmitter symbols. So at the point you receive the data, it got entangled together by the channel matrix H, which give you a linear effect, not nonlinear. And then you also got noise. And now in this talk, we'll assume the noise to be IID Gaussian. And the problem is that given that we know the channel, I want to detect this binary vector, n-dimensional, okay, n-dimensional, from the observation Y. It's a very classical problem. When research students today learn about MIMO detection, they know about this multi-input, multi-output system, or multi-antenna system, or maybe multi-user system serving 4G, 5G, etc. Now, but in fact, even in the old days, 1970s, when you have about digital communication, there is a problem called channel equalization for single antenna problem. Now, that will turn out to have a very similar model that we will see here. Okay, so it's a very classical problem that has many decades of history, if you talk about when we started to study this problem. Now, since this talk is about deep learning, perhaps we want to first of all take a look at what is the machine learning perspective to solve this problem. Now, the problem you have is very simple. You want to have a classifier, now which most likely will be DeepNet into today's standard. It's a nonlinear function. It takes observation Y. It takes the channel matrix H and output binary, okay, n-dimensional binary vector, such that this output should be as close as the true X as possible. Okay. Now, in terms of history, the earliest paper I can find is 1989 by Gibson, Su, and co-al. Now, at that time, their viewpoint is a lot simpler. Now, at that time, people don't. We mostly worked on linear detection, which in machine learning language is just support vector machine or linear classifier. Okay, so now how to read this picture? Imagine there's two elements here. It's 2x2 system. So you look at observation on dimension 1 and dimension 2. So there are a lot of points here now, which comes from different possible combination of binary. Okay, so in one version, you think like, how about using linear classifier to classify two possibilities? Well, actually, there are four possibilities. Right now, I realize that. Now, when you use neural network, what you want to do is to have a nonlinear decision region. Okay, so you want to use neural network to build a nonlinear decision region, so that hopefully, from a classification viewpoint or pattern recognition viewpoint, you would do a better job because you use nonlinear classifier. Okay, so now, so that is the starting point. Now, but here are some of the basic questions. If you want to do machine learning, you need data. Okay, you need Y, you need H, and you need X as your data. And we don't have training data, right? In image processing, there will be ImageNet, which is many different people's faces, very difficult to acquire in the beginning. Now, but it turns out that we don't need to worry that much about it. Now, one version to go is that you just use this model to synthetically generate your training data Now, in that sense, you can generate as many as you want, like using some typical assumption, IID uniform, IID Gaussian, etc., etc. Even for the channel, you can either use IID Gaussian, which may be sort of oversimplified, but academic researchers very typically would use it. Or if you work with industry, you can ask them for a channel generator to generate it. Okay, so in that sense, you can get a lot of training data to train your classifier. Now, but before I talk about state of the art, now I should mention that using neural network has been considered in around 1990s, but it never became a mainstream. And in fact, when we moved to 2000s, we have been much more interested in using model-based method, highly efficient techniques to deal with MIMO detection. So there has been a while where people are not all that interested in using neural network. But of course, like the application in speech and image processing, it will turns out that once we step to 2020 or a little bit earlier, it will become hot again because deep learning is everywhere. Now, but before we talk about how this renewed interest of deep learning for MIMO detection would be different from the 1990s, I first of all want to step a little bit to talk about state of the art back in the 2000s. Now, back in the 2000s and all the way almost to 2015 or something like that, now researchers, including myself, would be most interested in this so-called maximum likelihood MIMO detection. Now, this is only the consequential formulation of maximum likelihood. The original one should be the maximization of likelihood function. But it turns out that if you have IID Gaussian noise, this is what you have. It's a high-performance approach. From detection theory point of view, it guarantees you the minimum error probability of detecting the true simple vector. However, being a high-performance approach, it also has a serious problem. This optimization problem is an integer least squares problem, which is computationally very hard, and people know that it is NP hard in general, which means that when problem size n is huge, it's very difficult for you to find the globally optimum solution with reasonable computational efficiency. Now, despite that, researcher has been very into this problem. We simply love it for some reason. And for more than a decade, researchers either from computer science, over combinatorics side, optimization, I was talking about continuous optimization, statistics, such as message parsing, and also signal processing. Many researchers have shown tremendous interest in solving this problem, not just because it will deliver you a high-performance result, it's also that it gives you a very beautiful fundamental problem to work on with practical utilities. And that results in numerous MIMO detection methods that even experts couldn't explain in a few words or requires a tutorial for more than 3 hours. But of course, I'm not going to do it. But still, I want to recognize history a little bit by quickly mentioning what are some of the best approaches that has existed. Now, one is speed decoding. Now, speed decoding is a little bit over combinatorics or computer science size. Very simply speaking, or very roughly speaking, it is an exact solution for solving this combinatorial problem using branch and bound search. Now, by empirical experience, we found that these methods run very, very fast if the problem size n is not that large. Okay. In fact, many methods wouldn't even stand a chance. Okay. I had a lot of experience back in 2000s. You would not stand a chance when the problem size is not that large. When the problem size is not that large, I would recommend you guys to try speed decoding. Now, but unfortunately, if you want to try large-scale MIMO, n can be huge, more than 100, no way. If you run speed decoding, it will become frozen, okay? It suddenly stops for, let's say, a week or something and never give you an answer for that. And even more so, people can even prove that the computational complexity, even on average, is exponential with respect to the problem size n. So it works well for small size n, but not for large scale n. Another approach which became very popular in the 2000s is convex relaxation. Now, you don't talk about exact solution. You just want to do approximation, and you do so by leveraging on convex optimization. The simplest one is, of course, to relax my binary set with Rn. No constraint. The result is this square or zero forcing. Okay, so easy. Now the other one, which is more powerful, then, is to replace from either -1 or 1 to between -1 and 1. Okay, so you relax it as a box. People have been talking about it in early 2000. And finally, the other one, which cannot be easy to explain, is semi-definite relaxation, which was my PhD thesis, by the way. It used semi-definite program, a convex optimization problem, to approximate this problem. Works extremely well, has strong relationship to box relaxation and even unconstrained relaxation, and has polynomial time complexity. Now, there are also other methods, such as lattice reduction by, there's a better reference. The lattice reduction was introduced by a computer scientist, Lenstra and Vance. Very beautiful ideas in combinatorics. Now, this one is also quite powerful. Another approach, which is not maximum likelihood, is to use soft methods, such as probabilistic propagation ways, such as probabilistic data association, approximate message passing. Well, this one is actually quite powerful by performance if you have tried it empirically. And there are many, many more. Now, but in all these methods, what we have noticed is that it's all based on model-based techniques, not by deep learning. Okay. All right. So now, question. Since I mentioned that there's so many research study on that, so MIMO detection must be a well-studied problem, right? Is there anything that is interesting and meaningful for researchers to continue to work on this problem? Now, my answer, this is only my answer, by no means all people's opinion. Now, one of that is large-scale MIMO. Okay, we still could not find a low-complexity, high-performance, large-scale MIMO after more than 20 years. We still could not, despite methods such as speed decoding. It has quite a number of very nice features, including the theory part. No, it don't even try speed decoding for large-scale MIMO. Convex relaxation sounds nice. It's convex, but solving those convex problems still take you quite some computations. And in practice, real-time implementation, that is still not that affordable. Now, another reason, now this is a new problem known as coarsely quantized MIMO, now which come from massive MIMO. Roughly speaking, they want to use very low resolution analog to digital converter to save money, to save costs when they want to implement massive MIMO. Now, the new challenges that arise from this coarsely quantized MIMO is that a lot of good ideas that we learned in the past, such as speed decoding, semi-definite relaxation, the concept don't apply. Okay, so you have to completely revisit the idea when you work on coarsely quantized MIMO. All right then. So let's move a little bit faster. Now, so I almost done with the background review of MIMO detection. Now, let us talk about deep unfolding. Now, which will trigger the renewed interest of neural network for MIMO detection in 2017 in an algorithm called DATNet. Now, what is deep unfolding? Now, the idea is, simply speaking, you take a model-based approach, look at the algorithm, presumably iterative. You see this as a deep net and try to learn a better deep net. Okay, It was introduced for sparse regression by Gregory and LeCun in 2010 and has become very popular since then. Now, my review, so I'm going to give you a review on deep unfolding, and I would like to start with sparse regression because it's easy to understand. And then I'm going to talk about how this net work, and then I will talk about my method. All right, so problem. I want to solve this L2, L1 problem. Okay, I give you a dictionary A, I give you a picture Y, and I want to find a sparse X that will do a best fitting. And from what we learned in compressive sensing, sparse coding, etc., one possibility is to consider a regularized least squares problem with the regularizer being L1, which promotes sparsity. So now when we work on this problem, typically it has a large problem scale. You don't want to call a general solver, convex solver. And one competitive approach to do this task is to look at first order methods such as proximal gradient method. Now, simply speaking, even assuming that you don't know what is proximal gradient method, the idea is easy. Look at here is like gradient descent, right? For here. Proximal gradient, just do one more operation to deal with this non-smooth or non-differential part to do this iteration. So essentially, you can see it as a gradient descent, okay? But with a little bit little twist to deal with the L1 term. And eventually, once you plug the gradient equation, and I have this notation as a nonlinear function, which is exactly the same as the prox function. It's called a soft thresholding function, and I'm going to give you a picture in the next slides. So you run this iteratively, okay? So this is the first order proximal gradient method. Now, observation. When you look at this proximal gradient, draw a picture on the flow diagram. It looks like a network for which here is a nonlinear activation function. The soft thresholding function, and this S is a little bit like I think the S here and W. So you have a bias, and then you have a linear combination with the period situation. So the idea of deep unfolding is really I see this proximal gradient as a neural network. So what I want to do then is that how about I take those network parameters, every one of them, and also the width of the nonlinear activation function as the trainable parameters. That's what machine learning call them. So you want to use data to learn all these parameters so that you will learn. I will not say you will. You hope you will learn a better network than proximal gradient. So that is the idea. Okay. So this is how Gregory LeCun back in 2010 did it. Okay. But one thing I need to emphasize is the following: when they train this deep net, they train this for a fixed A or a given A, the dictionary. They didn't do it for any given A, okay? So which means that while proximal gradient method, once you go back to the previous slides, is a model-based method. Anytime you change the dictionary A, doesn't matter, I'll just do the same job as before. But since you are going to do this so-called untidying operation, replacing this structure as a matrix W and net, and then you train it from data. When you do it this way, it only makes sense for a given or specific A. Okay. So I'm skipping a few of the details here now, but one of the advantage we notice is that when we do this deep unfolding of proximal gradient. Now, in terms of performance, it is that given the same performance level, it requires much less number of iterations or layers to do the same job. So computationally, or in terms of complexity, it saves a lot. All right then. So this is the idea of deep unfolding in sparse regression, and researchers in the domain of sparse regression then look at many different other types of algorithms such as ADMM and even non-convex algorithm to try to do deep unfolding and see whether they can find a better network. Now, but we are interested in MIMO detection. So how did this first work that net did? Now, the idea intuitively goes as follows. I'll just recall you, this is a MIMO detection problem. Now, the first thing to learn is that they actually consider, my apology, they actually consider non-convex gradient projection, gradient descent here, and then you project it onto the binary data set. Okay, so the -1 binary variable, which is easy, is a sine function. Okay, so it's a non-convex gradient projection method, but be careful, there is no guarantee of convergence to global minimum. In fact, from a continuous optimization viewpoint, any binary vector is a local minimum. Okay, so don't even talk about convergence to a local minimum. Any algorithm will converge to a local minimum, by the way. All right, so it's very intuitive, if not heuristic. In deep unfolding by the authors of that net, what they are considering is that they will apply deep unfolding. Okay, taking the non-convex gradient projection structure you see here to see if we can find a better detector as a deep neural network. Now, but the thing I mentioned, but one thing I should mention goes as follows: when we do that, we want the deep net to work for any given channel, not a specific channel. Now, in the old days, such as a telephone line, if that line is going to be here for a while, so yeah, I think it's okay. You can train your deep network for that particular channel environment, and use that deep net like forever. Now, but in mobile channel, it changes from one epoch to another. So you want to train a deep net that will be flexible enough, universal enough for any given channel. So in that regard, I should also tell you that back in the 1990s, when people tried neural network for MIMO detection, they basically consider fixed channel, not any given channel. So our modern days renewed interest has a difference here. We want to deal with any given channel. Okay, back to the context. Now, the idea goes as follows for DeepNet, intuitively speaking. So this is the non-convex gradient projection. So you want to apply deep unfolding, untiding things. Now, a few things you would untie. Sine function, you untide it as a soft sine function, okay, parameterized by t. When this t changes, it will change. Simply speaking, it is a creeping function with a different scaling. Okay, so you control this this scaling, and you also add something some linear operation, just like making it more general. And this is these are trainable parameters. Then you form your network structure, and you use data to try to train all these W and TK. Okay, for each of the layers, and then you're done. Now, of course, what I'm talking about here is just a simplified version of the story. The true deep net used by Samuel Diskin and Wiesel is more complicated. They even now I don't know whether there's an easy way to talk about it, but simply speaking, inside this structure, they put another classical renewal deep multi-layer perception structure inside in a way I don't understand, honestly, and then to make the structure more general. And this is a picture, I guess no one understands it, but anyway, they just make the system, the structure more general. All right then. Now, and then after this 2017 work, it received a lot of attention, like unfolding gradient descent. You got a number of words. Some try high order symbol consideration. Some try overloaded MIMO, conjugate gradient. The other side, some people try approximate message parsing, and also even considering some other methods such as successive interference cancellation as one of the possibilities. Okay, so I think in the following years we will see more and more such research, and sometimes it's hard to compare because not all of them would like to put their source code on GitHub or any other website. All right, so it's almost half an hour, and right now I want to introduce my method. I hope it will not take you guys too long. Now the idea is simple. Now, since we talk about deep unfolding being some manipulation of model-based method, I first of all need to introduce a model-based method. Now this is my method, the original MIMO detection problem. I'm going to reformulate the problem this way. First of all, I do something like box relaxation, relaxing from either -1 or 1 to between. Okay, so I form a box here, but I would like to put a penalty, which is non-convex. Now, it's a penalty term to say that I want this x, each of the xi's, to have large amplitude. When I force the amplitude to be large, intuitively, because I also bound each of the x between -1 or 1, eventually, if I'm able to force it to its amplitude, the largest, which is 1, it should be either -1 or 1. Okay. Now, in fact, you can even prove that these two problems, the original ML and this penalty reformulation, are exactly the same. If you give me a sufficiently large lambda, it's even finite. Okay, it is even finite. Now, so you form a non-convex problem this way as an equivalent reformulation. You have a convex constraint, lies. You also have an objective function that is differentiable or smooth, but you have a non-convex objective function because you put a non-convex penalty here. Now, but the starting point can go as follows. In recent years, in signal processing, machine learning, etc., we have a lot of development about this so-called non-convex optimization. So we can simply pick a machinery to try to tackle this problem and should give us at least a reasonable local minimum. Well, that's at least what I hope. And so we did it. But is there a problem? I mean, now, of course, there is a problem. Now, the first thing is that I didn't say much about this penalty parameter. I only say that if you give me a sufficiently large number, it will be fine. Now, but it turns out it's not that fine because one problem, you could get stuck in local minimum. Now, this is a picture. For the moment, forget about this blue one. Now, this is lambda equals 0, which reduces to box relaxation. I gradually increase it, improves, and then increase it to lambda equals 10, which is green here, improves. As I increase it to 100, it suddenly goes up, and even worse, as I increase lambda to 1,000. You might question why. Now, the numerical operation, the numerical observation is that you get stuck in some really bad local minimum. So that is why. So on the one hand, you want lambda to be large so that it is closer to ML. But on the other hand, when lambda is getting too large, the problem is getting more and more non-convex in a way, and it's easier for you to get stuck in bad local minimum. So that is the problem. Okay, so I mentioned that already. You choose a small lambda, or even lambda equals 0 is convex, easy to solve. You can get the global minimum, but it's far from ML. You choose a very large number, it's non-convex. In fact, intuitively, it's getting harder and harder as you increase number, but it will be closer to maximum likelihood. So here comes the question. How about gradually increasing lambda? Now, let me give you an illustration on the landscape for two-dimensional case, which means that I only have x1, x2, and that's it. This is the objective function contour in the beginning. The gray area is the box, okay? Remember, I constrain x to be between -1 and 1. So as I increase lambda, all right, it seems to get up a little bit. I further push it, then it goes to the boundary, and then further increase it, then I force the solution, the globally optimum solution, to a binary point. All right. So this is the idea. And the very key idea of today's talk, I want to track the solution path. Okay? I want to track the solution path. And now I use the intuition that perhaps the landscape doesn't change a lot. Actually, it does change a lot here. Okay, I hope the landscape would not change a lot. So I can gradually track the solution path, what we call the homotopy path, as the solution, so that I can gradually track the solution, and then gradually get to the global minimum. Now, the intuition is that if the global minimum in the beginning, lambda equals 0, which is convex, and then to another, is not that far away, I could actually use the previous one, use gradient descent to get to another, gradient descent to get to another, so on and so forth. So if I follow this path, assuming that I would be able to, there may be a chance I can get to the global minimum. So this is the idea of homotopy optimization. Okay, so a pseudocode or pseudo algorithm goes this way. I start with, say, lambda equals 0, solve this problem, which is box relaxation, and then every time I increase lambda, and then I try to solve this problem. I hope it will be global minimum, but actually it may not. So hopefully, well, I can only hope for it, and I do it by gradient descent using the purest x as the initialization, and I keep on increasing, repeat this until I'm okay. Then I stop. So that is the idea of this so-called homotopy optimization. Okay, so when you do this homotopy, gradually increasing lambda, actually the performance is pretty good. Okay, so now I need to speed up a little bit. Now I only want to tell you one thing. Don't think this homotopy optimization is new. In many different contexts, although they are using very different ways to do it, such kind of a gradual transformation of homotopy is quite common, even in deep learning. Now, but of course, for this particular problem, you need to provide a very specific way to do this homotopy of transformation. So perhaps that makes the difference with our current work. Now, I'm getting close to telling you how I'm going to do deep unfolding. Now, but as a fundamental signal processing people, I love to provide interpretation, connection, and explanation. I really love to do that. I don't like always telling people that my algorithm's performance is better than who and who and who. I always outperform who and who and who. I always love to tell people that there is certain connections. So this is what we managed to find, as it turns out. Now, I would not say this is an explanation. I would say this is a connection. To better explain how this homotopy is happening. Now, suppose you look at this maximum likelihood problem. You can reformulate the problem this way, okay? Box constraints, but with an extra constraint that says that the Euclidean norm of x has to be greater than or equal to n, okay? When you put these two constraints together, the only outcome is to have x to be binary, either -1 or 1 for every one of the elements. So the next thing you want to do is to do Lagrangian dual, okay? Now, some powerful methods such as semi-definite relaxation is also having a strong connection to Lagrangian dual. Now, Lagrangian dual is an approximation of the original problem. Okay, so in this particular Lagrangian dual, your domain is the box. And then this is a Lagrangian, and this is the formulation over here. Now this is the Lagrangian variable where you deal with the constraint into the Lagrangian. Now one thing that is very beautiful is that you can actually prove that these two problems are not, this Lagrangian dual is not approximation of this. In general, it is Lagrangian dual is nothing more than an lower bound approximation of the original problem. But for this particular problem, you can show that they are, in a sense, equivalent. They're equivalent. Okay? So which means that solving this problem should get you to the global minimum of this. So now what you're trying to do with this Lagrangian dual, which is convex, although there's something strange right over there. I'm not going to tell you what it is. So suppose you deal with this convex Lagrangian dual problem by subgradient descent. Sorry, subgradient ascent, which is here. Where here is actually the subgradient, where you get the subgradient by solving this problem here concerning how you compute the dual function D. Now, when you look at here, the Lagrangian dual function, well, isn't it the homotopy problem? The panel, or more accurately, the non-convex penalty problem we were talking about, it is exactly the same. This subgradient ascent even tells you how to increase your penalty parameter lambda. So homotopy method, now this is the interpretation from a Lagrangian dual point of view, that your Lagrangian variable is homotopy penalty parameter. If you want to have an update rule for your penalty parameter from a homotopy viewpoint, you can look at it using the Lagrangian dual subgradient ascent. All right. So this is the interpretation. Although there is something not quite right. I'm not going to tell you what it is, but let me continue. How to do deep unfolding. I can explain to you in one page. Although Ming-J's work is definitely more than one day. It took a while with many experimental experiments to finally identify what's going on, and eventually we decide to work on this particular, take this particular form. Now, when I do this homotopy method, let me go back to the pseudocode here. Every time you gradually increase lambda, and every time you want to handle this problem, it should be augment by a descent method, and I choose a projected gradient method, accelerated version of it, to handle this part. And when you do it, very roughly speaking, it will take this form. Okay. First of all, this is like gradient descent, and you will project it to the box. Okay. Don't worry about those details. Once you put the gradient in there, you'll see a bunch of things. Okay. And we even consider accelerated projected gradient, so it's even a little bit more complicated here. But simply speaking, beta is the step size, alpha is the extrapolation coefficient responsible for making acceleration, and you also have this POC, which is a crimping function, and the nonlinear activation function from a viewpoint of neural network. Okay, so this is a system flow diagram. You have four variables, scalar variables. Sorry, three variables originally: beta, lambda. Lambda is the penalty parameter, alpha. Now, but what we are going to do is that we will release them as four independent parameters in the flow diagram, and we learn them from data. And yeah, that's it. That's how we build the deep unfolding network. All right. So let me show you some simulations. Perhaps we'll skip the details for the moment for how I train the deep neural network. Now, results. First of all, I look at 4540 MIMO system. You'll see a red line, lower bound. Now, this is a fundamental lower bound that no algorithm should be able to go better than this lower bound. So if you are able to approach it quite closely use linear optimum. Who can do it? Sphere decoding, okay? The exact search method. Semi-definite relaxation also managed to do that.
Okay.
And who else can do it?
Okay.
HotML, Homotopy Optimization, maximum likelihood, which is the method we previously talked about, but this one is not deep. Okay, it is not deep. It's right over here, which is also getting extremely close. I will always say that it's pretty much getting there in terms of performance. I mean, near optimality. Okay, so yeah, for 40 by 40, we are doing quite reasonably well. The deep counterpart is also doing quite well. Okay, is right over here, which is close to sphere decoding. And the state of the art, DetNet, the first deep unfolding network. Where is it? Let me see. Oh, it's over here. So it doesn't work that well in this 40 by 40 scenario. Let me increase the size to 80 by 80. Now, DetNet is over here. And then semi-definite relaxation here. Now, I don't run sphere decoding anymore because I cannot run it. Well, our computer will get frozen if we run it, or you ask me for the simulation results for 2030. Maybe I can give you that. And yeah, but on the other hand, if you look at this homotopy ML and also the deep version of it, they are also getting quite close to linear optimality. 160 by 160, pretty huge one. Okay, now yeah, DetNet is getting worse. Okay, now actually they don't provide a source code for 160 by 160, but in GitHub they provided the source code for training. We try our best, but never managed to train a better network for DetNet. In fact, it's even worse than some very classical approach such as minimum mean square error decision feedback. And this homotopy method, semi-definite relaxation, still work pretty well. But interestingly, there's another competitor that is coming. That one is NAMA, large-scale approximate message parsing. Now, this is a pretty cool method. We find that for large problem size, this competing method is able to work quite well. Okay, so when the problem size is getting large, is also getting you pretty good performance. So it started to become a competitor to us. Now, if we even try 400 by 400, we gave up DetNet. Okay, couldn't train it, and deep version of our homotopy maximum likelihood, we are still able to do it and are delivering reasonably good performance. And as I also mentioned, we only use 20 layers for all of the previous examples. Okay, and for this example, we are also unable to run the convex method, semi-definite relaxation. Complexity being polynomial time doesn't mean that you can run it. Okay. You probably want the computation to be linear in 400 rather than Q 400 to the power 3. Okay, so we were not able to run that one. Okay, so and right now the remaining competitor will only be approximate message parsing that can get close to the linear optimum performance that homotopy are able to do. Okay, I'll skip this picture. No, but we also need to look at computational complexity. So we look at the flops count, the floating point counts with respect to the problem size n. Okay, so if you run sphere decoding, yeah, when the problem size is small, it's really competitive, but it grows like crazy. Okay, as problem size gets larger, don't even think about it. Even when problem size is starting to get close to 30. Polynomial time method, convex method, semi-definite relaxation. Where is it? Right here. Okay. Yeah, polynomial time, but still quite expensive. We are already using the most efficient method to implement it, but still no. And then as we try homotopy, not the deep one, blue here. Well, this non-deep method is by simulation results work quite well, but still take you quite some computations. After all, remember that every time you need to solve the problem again, okay? Wherever you increase the penalty parameter lambda, so that contributes quite a significant part of the complexity. And then NAMA, approximate message passing, doing quite well actually for this method. Although you should remember, for small problem size, it's not working that well in terms of bit array performance. And finally, we talk about this deep homotopy. It is right over here. Okay, so far so good. This deep homotopy ML by simulation results is getting quite good in performance, almost optimum, and computationally also pretty fast. Well, we use 20 layers, so I guess that's the reason for its efficiency. All right, so a very quick go for it. Now, this is actually a much more exciting one. Although if I present it, it will not be easier than using classical MIMO. Now, the same idea can be used to deal with one-bit MIMO detection. In one-bit MIMO detection, you get binary observation. Okay, it got sign here. You are using one-bit analog to digital. Sorry. Yes, one-bit analog to digital converter, okay? So the maximum likelihood problem, now this time the likelihood function, log likelihood function should be readjusted in this way, okay? So, but the whole idea will directly apply. We just change, well, in our in the previous method, you realize that I'll just use first order optimization. So in the context here, we will just use the same thing. It's only that in deep unfolding, we will need to do a little bit more untidying. Okay, this is handcraft work. I don't know why. I don't understand why. Making it a little bit more complicated will work. If you guys really want to ask why it works, talk to Mingjie after the talk. I'm not going to explain why. Because, yeah, I already said it. Don't ask me that question. Anyway, now I'll try to only show you one result, okay? Now in one-bit MIMO detection, we tried this 256 by 48. And unlike classical MIMO, you don't have speed decoding, you don't have lattice reduction, you don't have semi-definite relaxation, but you do have relaxation such as sphere relaxation, unconstrained relaxation, etc. Okay, and you also have approximate message parsing, although it's quite different from the previous approximate message parsing. Now, in terms of performance, we are here quite good. The non-deep and the deep one here. The rest of the methods are not as close compared to the performance of what we can do. All right, so I'm concluding. So in this talk, I try to show you an example with applying deep unfolding for the MIMO detection problem. What do I want to say? Yeah, deep learning is hard. Everybody wants to do deep learning. But don't underestimate the power and insight of model-based signal processing. For such empirical research, I think responsible research should be about reproducible research, providing source codes, etc., for people to experiment on. So we did. We provide the full set of codes in these links. So if you are interested, download it and give it a try. So that's pretty much about my talk. Thank you very much.
Thank you, Ken. Wonderful talk.
Thank you.
We have time for a few questions. So let audience to raise their hands and unmute yourself and ask your question if there are any. Chandra, please go ahead.
Yeah, hi Ken, this is Chandra here.
Hey, hi Chandra.
Yeah, just one quick question. So for these results, did you use multiple channel instantiations, or and also do you retrain the network for each channel instantiation? You may have said it, but I might have missed it.
Oh yes, actually we train it for universal channel. So if this page will help you a little bit, this is what we did. Every time we generate sample for channel, data, and observation. And then every time that channel will be different, and this is the risk function we train. So it's trained for general channel, not for a specific or fixed channel.
Okay, thank you.
So this is Sandeep. Okay, I'll let Hari ask his question. Hey. Hari, go ahead.
Ken, wonderful talk.
Thank you.
I wanted to understand there is a concept of stochastic resonance where the mean square error increases if a certain SNR increases. But here in this case, your BR increased for a certain lambda, choice of lambda.
Mm-hmm.
Now, is there any connection, or is there anything which you have noticed or you have thought about? The stochastic resonance occurred in the quantization problem, where a 1-bit quantization was used at the output of the or at the input of the receiver.
So let me better understand. You're talking about the problem of 1-bit MIMO detection.
Right.
Okay. So your question is about. Would you like to say that again?
Yeah. So in the 1-bit quantization literature, there was an observation that if you increase the SNR, the mean square error in the channel estimation, which could be a typical classical channel estimator, increased beyond a certain SNR. So it sort of decreased as SNR increased, and then at some point it started increasing. So I know that in your case it is it's different. I'm just trying to understand because for you, as you increase lambda in your problem, your BER increased beyond a certain lambda. It decreased first, and then it increased, right? So I'm just asking whether there is anything similar phenomenon which you have thought about.
Now, I'm not expert in this channel estimation problem, so my opinion could be quite wrong actually. Now my interest here is look at detection. Now it's somehow quite different. It's somehow quite different if I use my own point of view to look at the problem. Now there are two aspects of the question. One question is fundamental limits. Now, which there's not much no matter how good your optimization is, there is nothing you can have a breakthrough on the limits. Now, I have a feeling that the question you're asking is closer to fundamental limits. Now, which will be a different problem from this deep unfolding and homotopy optimization. Now, which is about that this is a problem I have. This is a problem I have. I just try to see whether I can get the best solution out of it. So basically, I'm an optimization people, not looking at the fundamental limits. If I first of all look at it from a fundamental viewpoint, I have a different point of view. Simply speaking, if in this 1-bit problem, you will have an advantage only when the problems, the number of binary vectors you have is a lot larger than the number of unknowns. Now, we can even prove it, okay? We have a little bit result that can prove it. So basically, I really want this channel to be a very tall guy or a massive MIMO. Now, in that sense, under certain IID Gaussian assumption with the channel, actually, it is okay. The performance will be good. Even when the signal to noise ratio is different. Now, so perhaps it doesn't answer your question, but I'll try to use my point of view to answer that aspect. Now, on the other hand, if I go to the algorithmic side or optimization side, is there any relationship with the oscillation behavior of the penalty parameter? No, I guess my answer, I would say I don't know. Now, one reason, once I go to deep, I actually let deep neural network to learn that penalty parameter lambda. So I don't know what it has done. So I was not able to answer that question. Although that's a very evil answer. Sorry, Harry.
No, I mean, it may be totally disconnected. I just, thanks.
Chandra has one more.
Yeah, I can. One more question. So
sure.
When one uses homotopy-based methods for sparse signal recovery, there is actually an analytical way of determining the next values of lambda that you want to use. And the schedule for increasing, so you actually don't solve it for every lambda, but you look at, you analytically figure out what should be the next value of lambda that one should use.
Oh, yes. I know
Is that possible for this problem, or?
The answer is no for the moment, but I hope future work can provide a better answer to this question. And this, I believe, is what we signal processing people do. Now, first of all, in L2, L1 sparsity, yeah, there are papers, as you pointed out, that can analytically even analyze how we should change the penalty parameter lambda from small to large. Now, but on the other hand, the problem they deal with is easier because the original problem is still convex. It is still convex. At least these are the papers I read, okay, where they will be able to have an analytical formula concerning how to adjust the lambda. Now, the biggest difficulty as we go to MIMO detection is really that it is non-convex. Okay, so that makes the analysis very difficult.
Yeah, right. Thank you. Yeah, it's a clear answer. Yes, thank you.
Maybe I'll ask. So there is one more question, but before that, let me ask a question. Ken, in all the simulations that you explicitly mentioned not to ask this question, but I'll do that anyway. So
Go on.
In the DeepNet methods, the simulations that you showed, you mentioned that the error is saturating and it does not perform well. So just curious, why does your method work? Is it because you have very few parameters that you're training, or is it because of the homotopy approach that you're using?
Now, if you want to find a reason, okay, to confirm your theory, I think this is the reason. This is a reason. I would not say the reason.
Okay.
But empirically, this seems to be the case. That seems to be the case. I mean, DeepNet, even when you train it, because the structure is more complicated, it takes longer time to do it. So, so in a sense, I should also mention one more thing in that regard. I should emphasize that it was only us who failed to train DeepNet. Maybe someday somebody who have more GPUs, servers, computation, maybe one day they manage to train it, but we failed to do it, and we didn't see existing work that can do it.
Okay. So there is one more question. Maybe we'll take this as a last question from Swati. Go ahead.
Good evening, sir. So thank you for the talk. It was a very nice talk. And
Thank you.
I just wanted to ask one question. So in this 160 cross 160 simulation results, the graph shows that deep hot ML performs marginally worse than hot ML. But isn't deep unfolding what you do to improve the performance? So that is what I'm not able to understand.
Sorry, it seems to be there seems to be a little bit network problem. Would you mind if you can rephrase the question a little bit again? So which method and which method? There was a little bit network problem there.
Sorry, sir. So what I meant was that hot ML, the proposed, and the deep hot ML, those two, your proposed two methods. So in the graph, it shows that the deep hot ML performs marginally worse than the hot ML method. But isn't a deep unfolding what you do to improve the performance?
No. Okay. I would not be able to answer that question once again. Now, because once you now, honestly, to be extremely honest, I would not even be able to answer what happened to homotopy maximum likelihood. Now, this is because, well, the intuition is to try to track a solution path, okay? Long time ago, yeah. I try to track the solution path. I am not able to tell you guys that I will always be able to safely track that homotopy path. It could be, in some of the simulation results, it fails, okay? So I can't guarantee that part, no. Now, deep homotopy, that is even more so. We don't know what will come out in the training process. So we can only observe, but we cannot say much about it.
Thank you.
Okay, so I guess yeah, we can stop the Q&A here. So let me, on behalf of the department, thank you, Ken, again for taking out your precious time in spite of.
Oh, no worries.
Yeah,
my pleasure.
Yeah, thank you very much, and yeah, it was a very nice talk. And hope to see you sometime in the near future in person.
Physically.
Yeah, physically, yes. Yeah. Thank you all.
Thank you.
Yeah, thank you. Yeah. Thank you.
Thank you, Ken.
Bye-bye.
Bye. Thank you. Bye.